Good morning and good afternoon, everybody. It is great to see how many have joined us here today. And welcome to this webinar hosted today by Intertek. The speaker today is Rich Bychek, Global Technical Director, Transportation Technologies from Intertek. Rich has over 25 years of experience in product development and validation testing, 17 of which has been spent Intertek. Rich is experienced in the areas of energy storage, audio equipment, and EMC testing. As Intertek's global technical lead for electric vehicle and energy storage, Rich sits on several SAE, IEC, UL, and ANSI standards panels. He holds a Bachelor of Science in Electrical Engineering from the Lawrence Technological University in Southfield, Michigan, and is based at the Intertek facility located in Plymouth, Michigan. We encourage you to ask plenty of questions at any point during the webinar. Please do type your questions into the Q&A box you will find at the bottom of the screen. At the end of the presentation, we will present your questions and answer as many as possible. It is an absolute pleasure to have Rich with us today, and I would like to warmly welcome Rich to now take control and begin the session.
Thank you, Martin. Yes, hello, everyone. Good morning, good afternoon, good evening, wherever you are. Thank you for joining us today. Again, my name is Rich Bychek with Intertek, and today's topic is propagation testing, specifically cell and battery abuse trigger methods. As I work for a testing laboratory, looking at this somewhat from the laboratory perspective, but also understanding some of the pros and cons that we've seen in trying to implement variations of lithium-ion battery propagation tests. I'll start with a brief introduction on Intertek and our service offerings in this space, and then we'll look into the main topics today, a bit about the background of the concerns about propagation specific to lithium-ion batteries, the test standards, where do these these propagation concerns turn into actual requirements out there in the field for different industries. Then, as I mentioned, from a lab standpoint, especially, how do we actually implement these tests? Looking at the various common methods of cell and battery propagation, test methods, and triggering, and then again, some of the specific challenges we've run into, issues that we've seen, again, from the testing lab standpoint, but also just the implementation standpoint of trying to actually conduct some of these tests on some small to very large systems. So Intertek, we are a global assurance testing inspection certification organization, ATIC as we call it. And these assurance services cover multiple industries around the world. Within what we call our products divisions and our automotive or transportation technologies group and electrical groups, we have a dedicated laboratories that focus specifically on energy storage and battery testing. And those are the ones you see here. And those are just a handful of labs out of over 1,000 sites we have globally. As mentioned earlier, I sit in the Plymouth, Michigan facility, which is the center icon there in the North American part of the map. In Central Europe, we have a similar site in Kaufbeuren, Germany, just outside of Munich. And in the China region in APAC, we have similar capabilities in Shanghai. You'll see the other sites there, Sweden, the UK, here in North America, New York and Texas, and also just outside of mainland China, southern China and Guangzhou, also Taiwan and Taipei areas where we offer, a pretty wide range of various services from testing, certification, abuse, and consulting applications. So I mentioned testing. So of course, 38.3, which was yesterday's topic in the seminar we gave, which is your core transportation testing. Then in product certification work, the CB scheme, which is international certifications according to IEC standards. And then in North America, NRTL, or Nationally Recognized Testing Laboratory testing, where Intertek, we issue our ETL mark for North American markets. Core standards there, 62133-2 for your smaller portable battery systems, the UL legacy standard 1642, 2054, and then in larger systems like we're talking about mostly today, UL 1973, 9540, and their IEC corollaries. And those are the 9540 standard, and it's a test method. 9540A is really one of the heavy drivers for interest in propagation testing today, especially in North America. On the EV side, of course, this is an EV-centric broadcast. We have the abuse test according to SAE J2464, and different OEMs have their own, proprietary or lessons learned, if you will, in terms of how we would conduct propagation testing based on different battery designs, battery pack designs, custom abuse testing. So outside of propagation, any type of simulation or worst case scenario testing, and then of course more of the supply chain control in terms of performance lifecycle evaluations, just cycling batteries through calendar and actual charge discharge cycle aging. Safety tests specifically, again, everything from small hearing aid batteries up through megawatt energy storage installations. So we do have multiple sites around the world. I mentioned specifically here in the US in Plymouth, down in Texas, where we have a large scale fire test assembly laboratory, and then in Kaufbeuren, Germany, where we perform, again, a wide range from small through large scale certification and abuse tests. Obviously, these all require somewhat ruggedized facilities or remote facilities. You'll see some of these are outdoors, some of these are indoors, with various ventilation, health and safety measures implemented. But aside from just the core battery abuse tests in the EV space, we also have to consider that the batteries are an automotive component, subjected to all the same environmental extremes and durability concerns that we have for all other electronic components or hard and soft trim components. So that includes your altitude, your dust, your salt, temperature, and humidity, and of course that cycle durability. So a wide range there, depending on your needs, whether it's performance, reliability, safety certification, or those worst case abuse standards. We have a pretty extensive portfolio in our centers of excellence for performing those tests. Aside from the testing, failure analysis, and advisory or consulting services, we have teams specifically expertise in the US and in Sweden that focus on failure analysis, evaluations, as well as supply chain assurance in the battery space. And I showed the example here of a disassembled cell that can be part of a failure analysis field return. That could also be part of evaluation of potential manufacturing defects, or even just A to B comparison testing of various suppliers, again, from a supply chain assurance standpoint, just to look at the quality of manufacturing from your cell and battery module suppliers. So taking, your core ISO 9001 and, general quality system concerns, being the baseline, we also look at the best practices from a technical standpoint in terms of manufacturing and developing battery systems. I mentioned the US and Europe as far as expertise. However, we have a lot of, if you will, boots on the ground, inspectors, auditors, assessors in the APAC region, knowing that a lot of the production capacity sits there in APAC, and especially over the last 2 years where travel is a bit of a difficulty or a challenge, having those resources dispersed around the globe helps us to support this market. So with those introductions aside, again, I'll have my contact information at the end of the presentation. Please feel free to reach out to me if you have any needs or concerns or potential challenges that you're dealing with. I'd be happy to talk to you through those. But today's topic, propagation testing. We'll get into that now. First of all, propagation concerns. Let's talk about, just a little baseline here. What is propagation? We talk about propagation testing and making sure we're all talking about the same thing. This is related to thermal runaway. And thermal runaway is where the heat produced from a cell exceeds the input energy. So this means that even if you remove an external stress such as temperature, fire, overcharge, short circuit, etc., electrical, mechanical, or environmental stresses, the battery will continue producing heat on its own. So that's a thermal runaway. It can't be controlled. It can't be limited from external sources. You may be able to, at some point, provide the external, the opposite, of cooling or fluid, etc., to cool the battery to try and stop this effect. But without additional external stress, the battery is going to go basically catch on fire, potentially explode. We look at propagation, meaning that when a single cell goes into some level of thermal runaway, that it propagates or cascades from that cell that was already damaged or compromised to the adjacent cell, which may or may not have had a similar damage or compromised situation, but rather just the heat and fire created from that first cell actually causes the second cell to have a similar reaction, and then potentially you cause a chain reaction throughout the battery. So that's propagation. We do expect, if you will, from a statistical standpoint, individual cells across production are eventually going to have some sort of manufacturing defect, premature aging, potentially a design issue, but more likely something where that cell is not representative of the majority of the manufacturing population. But even with a very low level, talking about in the parts per billion or parts per million, knowing that you could have thousands of cells in every individual EV or stationary battery pack, that means that over the course of a few thousand batteries, you're probably going to run into at least one, if you will, bad cell that could go into thermal runaway. That's an expected reality, that you'll have a single cell going to runaway. However, what is not the expected or acceptable reality is when those do propagate throughout the battery, creating a large scale fire that basically goes beyond the case of the battery, requiring some sort of external firefighting or potentially causing external damage beyond the casing of the battery. Of course, today we're talking lithium ion specifically. The same concerns could occur in other battery types, but typically, of course, because of the type of heat release, the type of energy content and density within lithium ion batteries, and the proliferation of lithium ion for, call it, the current and upcoming generations of electric vehicle batteries and stationary storage, this is, of course, the area of focus. So what are your main causes of the initial cell level failures? I mentioned a few of them earlier, but we start with manufacturing defects. This is something that occurs during the manufacturing process. It may be a design issue in terms of how we've designed either the battery itself or the cell itself or the manufacturing process itself. And there have been examples of that over the past several years of batteries where just because of the design intent, you ran into inherent issues in terms of how the battery's internal components fit together, leading to some premature internal short circuits, hot spots, poor thermal management, etc. Or you have some of the more, I would say, more common occurrences over the years. Some of the incidents that have occurred over the past 25 years or so, manufacturing defects where a contaminant made its way inside the battery, and that became essentially the source of an internal short circuit. So I keep talking about internal short circuits. Those tend to be one of the causes internal in terms of the mechanisms, is some sort of shorting mechanism between the anode and cathode inside the cell, allows for basically an unintended current path that creates heat and could eventually evolve into a fire and explosion. Next, you have aging effects. So, of course, manufacturing defects aside, that's usually what we'd call an infant mortality or an early failure in the life of a cell. But you have also aging effects. They could be a combination of a manufacturing defect, a thermal management issue, or a design let's say, weakness, or just from the aging of the raw materials within the battery, within the cell, that you actually, over time, create enough side chemical reactions that you build up pressure within the cell, you build up a dangerous concentration in the cell that could erupt into a thermal runaway event. Next, electrical abuse. So this is talking about usage cases. Typically, we're concerned with things like an overcharge event, meaning excessive voltage or excessive current outflow from the battery or inflow to the battery for charging, and then outflow in terms of short circuiting or over discharging events where you actually drive the battery beyond its 100% stated charge and down below its 0% stated charge. So when we talk about state of charge, that doesn't mean 100% of the physical capacity of the battery and 0% of the physical capacity of the battery, but rather 0 to 100% of the usable capacity of the battery, where if it's discharged at 0%, you should be able to essentially recharge it back to roughly 100%. And at 100%, you should be able to discharge that battery safely down to that 0. So that's really talking about an operational range of the battery, not necessarily the full capacity of the battery. And I bring that up because when we talk about short circuiting, we talk about over discharge, we talk about overcharge. It's where the battery could essentially go beyond 100% state of charge or actually driven below that 0% state of charge. There's still energy content available. There are still reactions that can occur that aren't intended within the battery that can build up gas. So electrical abuse is one of those major concerns that can be somewhat addressed, at least from engineering controls. Mechanical abuse in the EV space, we consider, first of all, things like a crash event. Vehicles are impacted. You have repetitive impacts, foreign objects hitting the battery, other causes that essentially would penetrate or otherwise deform the battery physically, such that you could trigger some sort of thermal event or internal short circuit. Thermal abuse simply is just overheating the battery, where you actually drive the temperature of the battery such that some of those other side reactions, other chemical reactions that are unintended within the battery can be triggered just by the temperature alone. And that also would then cascade within the cell that even if you took away that external heat source, the battery reaction has already started. It's creating its own heat, and therefore it can propagate or at least go into a full thermal runaway. Now, a little of these one by one, manufacturing aging defects. I mentioned internal short circuits before. Foreign objects or substances, again, manufacturing defects, things that can occur in the manufacturing process. Even if you have an ISO 9001 type of quality system, you still have cases where you're not maintaining, for example, a full clean room type of environment. Maybe as a contract manufacturer, assembling circuit boards, you're at a cleanliness level that is more than adequate. However, when you're dealing with these open containers of cells and you're assembling them, that level is still considered unacceptable. And even smaller particles that can make their way into the mix and into the battery could essentially become a shorting element within the battery. So typically when we're talking about manufacturing defects, our concerns are contaminants or unintentional short circuits where you've essentially pinched or penetrated layers of the anode and cathode such that they create a short circuit path inside the battery. Just showing here the image, what the effects of some of these thermal runaways can be at the cell level, or even some of the aging effects over time. You create either that short circuit path or you have other chemical reactions occurring within the battery because of that manufacturing defect or that foreign substance in there. And those reactions are non-reversible, so they build up pressure. They can't be resolved or reversed such that pressure is somehow reduced again. So you eventually get to a point where that pressure and heat build up enough that you rupture or break open the cell. And depending on how quickly you do that, that could include fire and heat, or it would just be more of a performance type of failure. Talk about some of the other abuses, the mechanical, electrical, and thermal abuse. I mentioned before, exceeding temperature, exceeding current voltage, either in the positive or negative direction. And the image on the side here, which comes from some of the IEC standards, showing that operating range of a battery in both current and voltage, and a third, essentially, if you made this into a three-dimensional image, you have a temperature range as well. So here, the temperature shown across the lower axis here, but you would actually have a combination of current, temperature and voltage all have to be, within a certain envelope to make sure that the battery will function as expected, that a charging event can allow the battery to get to its maximum available charge, and a discharging event is going to allow it to go down to its maximum available capacity and be reversible. So when we go outside of these ranges, we lose that confidence that we can maintain the reversibility. We can cause some of those chemical side reactions, or we drive the battery to create more heat than it's able to dissipate, and therefore, when it has too much heat that it can't dissipate, that again can be one of the raw causes of a thermal event or thermal runaway. Mechanical abuse examples: crushing, as I mentioned, in a crash event; penetration of foreign object, a nail, a spike of some sort, even the enclosure of the battery during a crash event, that it actually physically penetrates the cells, and water exposure. So water being just another environmental impact, although we don't think of it as such a stress event. However, water can be potentially conductive, and if it penetrates or enters the battery system at least the external to the cell level, you can cause an external short circuit across cell terminals. So even within a full battery pack, if the main terminals are protected enough from a water event, if you were to flood the vehicle or it's in a rainstorm, individual cells inside the battery pack, if enough moisture built up in there or condensed inside the battery pack, you could cause a short circuit across the terminals of individual cells. Electrical abuse, I mentioned overcharging, potential short circuits. Short circuits aren't always just shorting the positive and negative terminals together of the battery with an external source like we do in transportation. An external short circuit could be a motor being seized within the vehicle, so that in an electric vehicle, for example, so that you're trying to drive current to push the motor to drive the vehicle. That motor becomes an essential short circuit load to the battery. And if you don't have the right protections in place, you're allowing an unsafe amount of current that's going to generate excessive heat. Could drive the battery below that 0% stated charge, but more likely it's the actual heating effect there that's going to drive the thermal runaway. Overcharge has a similar situation, especially over voltage. Again, the voltage range of individual cell reactions is in that 3.5 to 4 volt range for most lithium-ion chemistries. Once you exceed that by any amount, again, you trigger some of those side reactions, other chemical reactions occurring within the electrolyte and across the electrodes of the battery that are not intended. They don't result in the transfer of electrons. Instead, they result in the buildup of gas and pressure and heat within the cell. And thermal abuse, of course, excessive temperature that could be caused by one of the above mechanical or electrical cases, or just purely it's in an environment that's too hot, such as in a fire, which is one of the big concerns for stationary batteries. And of course, is a secondary concern, if you will, in a crash event, you have the crushing, you have the actual event itself, the mechanical shock that occurs, but then you have a potential for fire, especially where you have hybrid vehicles, standard gasoline engine vehicles, where there is fuel sources, gasoline, oils, etc., that could also create a fire of their own that could then heat the battery such to a dangerous temperature. So understanding some of those main concerns of what can cause a thermal runaway event or propagation event to be triggered, how can we prevent them? First of all, I mentioned statistically, you're going to have a bad cell somewhere along the way, but manufacturing controls, design improvements, engineering out some of the potential causes of those manufacturing defects is your first line of defense. And obviously, as manufacturing prowess increases, as we get through more iterations of prismatic and pouch cells and different chemistries and different constructions, we build up these lessons learned, and we find out how to roll the jelly roll so that you don't pinch the corners. We find out how to seal the pouches so that we don't potentially cause a shortened corner within that pouch. We find out how to ensure a clean environment so that contaminants don't make their way in. Crimping procedures, etc., all can be improved. You're never going to get to a zero ppm or ppb number. Statistically, that's not possible, but you can get that number down to a very workable level, so that we call an acceptable level, that you're going to have maybe one in less than a million or more than a million occurrence of a single cell having a defect, but you get that to where additional controls will prevent that from becoming a propagation event. Maintaining cells within the operating limits. This is more of an engineering factor. Battery management systems, thermal management of the battery. Let's just maintain it within that temperature, current, and voltage range, and assuming that that vast majority of the cells which don't carry a latent manufacturing or aging defect, that battery is going to perform well all throughout its usable life. Eventually, it's going to reduce capacity, but that's a normal effect. And generally, reduced capacity by itself is not a safety hazard, but rather a performance side effect. Performance side effects are much easier to deal with than, of course, the safety hazards. Mechanical shielding. So we're talking about some of those mechanical stresses. How do we prevent the individual cells from seeing the effects of mechanical stress, like a crash event? How do we protect it by a more structured enclosure, et cetera? And then, of course, testing and screening. The testing, from a statistics standpoint, help you to evaluate when you start to maybe implement a design change that has a flaw in it, when you have a possible manufacturing defect, when you have a possible source of contaminant, you have raw material issues where an anode, a cathode, an electrolyte mix, something else within your raw materials, your incoming parts has its own defect. Again, this is more of a quality management system issue, but testing and screening in that case helps you prevent for some of those even low ppm rate issues from occurring in the first place, and then screening on the backside, so that even once you've assembled the cells or batteries, you're able to look for some of these issues, whether it's just from verifying the capacity, that you don't have some sort of internal short circuit already in the cell, some other measurements that can take place really at the factory. So before they even go out into the field, you've done some screening and some additional testing. It's not generally feasible to do 100% full teardown test on every cell, obviously, but sometimes some teardown analysis and actually removing cells from production just to do that full teardown to make sure that you're not trending towards an issue. Final note, I mentioned cells will go into thermal. It's going to happen statistically. You can't make it zero, but there are so many well-known ways and lessons learned that can help us get that number to a very low level. So propagation failures, and we're talking here first about cell level failures. How do we actually trigger an event at the single cell level? But what happens when that potentially propagates? Again, you get additional cells, adjacent cells to go into runaway because the first cell got too hot, and you don't have sufficient protection between the cells. You don't have sufficient spacing between the cells, or just the layout of the battery causes that any venting or any release of heat from one cell directly heats the adjacent cells. So that's your propagation failure right there. How allowing that individual bad cell to trigger the cell next to it. When we talk about a failure of propagation, even if that cell to cell cascading does occur within the battery pack, does the battery pack design or the robustness of the enclosure, for example, prevent that any propagation event, even if it does occur from one cell to a second cell or a third cell? Do you prevent that from escaping the battery? Do you prevent visible flame from escaping the battery? Do you prevent the external enclosure walls from getting too hot such that adjacent combustible materials could go into runaway or fire? And finally, is the event not self-extinguishing or self-limiting? If a cell goes into runaway and doesn't trigger the cell next to it, that's a self-limiting event. If a cell triggers a second cell, but that doesn't create enough heat to trigger a third cell, then you have, again, a self-limiting event, and you don't exceed the mechanical constraints of the battery itself. Even though the battery is no longer usable, it hasn't created a greater safety risk to the surrounding area, the surrounding batteries. Another failure would be in a design, a layout, in stationary systems, especially, do you not have the ability to externally extinguish that battery? You're doing all these things, protecting cells from each other, trying to build an enclosure that's robust enough to prevent fire from getting out. You're also often preventing fire extinguishing fluids, water, et cetera, from getting into the battery. So some of the same design features that help prevent propagation are also preventing extinguishing. So keep that in mind, that there may be a balance just in terms of allowing for the battery to be put out if it did go into propagation. Transportation concerns. We talk a lot about batteries as they're being used, going into temperature, voltage, current extremes. But during transportation, where you're not generally concerned with those elements, you're not heating the battery other than through the normal environmental conditions that we address in the 38.3 tests. But there are specific concerns that if a battery went into runaway because of a bad cell that was, if you will, smoldering, and it did cascade to adjacent cells. In an aircraft, for example, it would only take a few cells to create enough smoke or enough fire that it could bring down the aircraft. We have concerns of damaged batteries that's already been damaged in the field, repackaged for return or recycling. It's coming back to another facility. It's just going to be disposed of. That damaged battery works its way into the normal transportation space, and it's not, considered to be safe before it goes into that transport condition, and it could go into a runaway. Some of the more publicized events that have occurred in the field are from batteries that were compromised at one point. And because of the size of the battery, because of some of the engineering structure of that battery, the propagation was delayed, but it still did occur. So the battery was actually in transport already before the propagation exceeded the enclosure of the battery and caused an external fire. End-of-life batteries, again, less of a concern because generally speaking, you've reduced the overall capacity, you've reduced the available energy in that battery. But again, you have the potential for those side reactions because you're driving the battery below its 0% state of charge. You have some of the other aging effects or manufacturing defects are coming to the surface over time, so that you could still trigger a thermal runaway. But I would say overall, that's less of a concern at end of life versus things like damaged batteries or abused or stressed batteries that have been put in the transportation space. 38.3 testing, talked about that quite a bit yesterday. Really doesn't address propagation currently. It addresses some of the general temperature and electrical and mechanical trigger points of that could cause a thermal runaway in transport, but it doesn't really address what happens under an actual propagation event. If it occurs, does the battery self-limit? So there is some work in several committees, either UN, SAE, et cetera, in developing methods of evaluating self-extinguishment or packaging protection for thermal runaway events, but it's really not fully addressed yet in the transportation regulations. Consumer product concerns. Again, we're talking mostly electric vehicle here today, but understanding, there's a significant volume of batteries out there in the consumer product space. Many of them are built to different regulations, non-harmonized. I mentioned IEC standards, UL standards, et cetera. So even if they are following good practices from a quality system, maybe they don't know the nuances of a lithium-ion battery versus previous chemistries that were used in their products, or they're not following just general best practices for batteries because it's new to that manufacturer. Variability, of course, in product quality from factory to factory, country to country, raw material supplier to raw material supplier. Some of the current supply chain issues, you're suddenly switching to alternate suppliers that may lead to some of these other issues. I like to highlight things like non-OEM chargers. Use the example here in the U.S. The dollar store charger. It looks just like the form factor of the charger that came with your cell phone from the name brand manufacturer, from the Apple or the Samsung, et cetera. Those are certified chargers that comes with those phones. When you go to buy the replacement charger, that that exact replacement charger costs you $35, $40, but you see one that looks the same at the store for $1 at the register, so you pick that one up. That's a potential stress source because the controls may or may not be good enough to prevent that temperature, current, or voltage range from being exceeded in the battery. We expect that there are to be some level of protection within the batteries, but the more likely you are to present a stress source, present an abuse condition, present something outside of the normal handling ranges, the higher likelihood that that's going to make its way into the battery and cause an issue. Handling and abuse, I show the example of the cell phone here. I think we all do this. We've dropped these phones on concrete, we've dropped them in puddles, and then we go ahead and put them under our pillow at night to sleep, because it's also our alarm clock and our entertainment during the evening, or our music player, etc., while it's plugged in and charging. So there's a lot of concerns here that if a cell went into runaway, it's going to exceed the case of that. It's going to set things on fire. It's going to find nearby combustibles. It's going to find nearby people that can be injured or worse. So with millions of devices out there, we know we're going to see some level of thermal runaway occur in the field. In the EV space, I mentioned some of these concerns already. Crash and accidents literally add fuel to the fire. I'm showing the example here. Of course, these are, I think, full normal internal combustion engine vehicles, but hybrid vehicles or a full electric vehicle that's involved in a crash with another vehicle that has an internal combustion engine, you have the available source of fuel, gasoline and oils flowing through the engine. You've got hot exhaust systems. You've got a good mix of conditions that can trigger a fire, especially when there's a crash event between vehicles. And that fire alone could be enough of a stress source to trigger the battery or cells within the battery to go into thermal runaway. Energy storage concerns, we talk about stationary systems, often similar and much larger capacities than we worry about even in the electric vehicle space. These are often retrofits in older buildings. They're in the basement. Something like you see here, an array of batteries that a few years ago was all lead acid, and all you were really concerned about was having enough ventilation so that during normal charging, any hydrogen off gas could not build up to create an explosive atmosphere. Pretty simple to, relatively simple to implement a ventilation system that doesn't allow that air to trap in a pocket above the batteries. Secondary concerns are more about flooding, leaking of electrolyte that didn't necessarily cause a fire, but had other hazards. Again, some level of physical containment basin, if you will, to capture the volume of electrolyte that could spill from those batteries. Going back in the building codes, many of these battery rooms and facilities were built just for those concerns: leakage of electrolyte, venting of hydrogen gas. Venting of hydrogen gas is a very low concentration, so the equivalent of a mild circulation fan would often be enough to prevent or mitigate that concern. Here we're talking about during normal operation of the lithium-ion battery, it's not giving off any. It's not expected to give off any gas, but under a thermal runaway event, we do expect volumes of off-gassing, volumes of smoke from occurring. Even if there isn't a direct flame involved, the volumes of smoke are not going to be covered or handled by a small circulation fan that was sufficient for a lead acid install. So a lot of the building codes are really concerned with these retrofit installations or even new installations that are built according to old codes. How do we address those additional concerns? The volume of gas, the higher temperatures, the potential for explosion that can occur when you have much higher energy density batteries in the same volume of space that we previously had a solution for or a way to mitigate those risks. So understanding that as these are being implemented, certain jurisdictions are a bit more aware of the concerns. In the US, for example, where we have a very, if you will, disconnected system, individual municipalities have their own inspectors and fire marshals and codes, and you're reliant really on the individual experience of that inspector rather than national harmonized codes to evaluate the installation of a system. It's very easy for a system that shouldn't be installed to be installed. Similar to EV, Similar to consumer products, an array like this is hundreds of kilowatt hours of capacity, which means thousands of individual cells. And with even a 1 ppm rate or lower, you're going to have a single cell probably fail at some point within the life of this one battery array alone. And the hope is that the majority of those kind of failures are going to lead to a fairly benign event. The battery capacity is reduced, one module needs to be replaced. But on the other end of that, one of those single cell failures could cause the entire system to go into a propagation thermal runaway event, and you have a large scale fire that can't be effectively contained. Now, talking about all those concerns and the issues, it's worth understanding these are the reasons why we have concerns with doing propagation tests, finding a way to simulate or emulate those concerns. And if you understand, some of those potential concerns, manufacturing defects, aging effects, some of those mechanical stresses, there's even with statistical controls, those are somewhat random in nature in that you're not going to necessarily mimic a poorly manufactured cell by trying to artificially manufacture a bad cell. You're not going to get the exact angle of incident impact of a crash event by doing a single plane crush test. So it's very difficult to find ways to truly emulate all of those failure modes. So in the various standards, we still try to find ways to capture how can I at least trigger an event that's somewhat realistic, that's somewhat of a worst case, but is not overly arduous such that it's impossible to design a battery that could even be put into the field. The market demand tells us that these batteries are going to make their way into the field. They need to be used. We have applications for them, but we have to find a way to mitigate the risks of thermal runaway. I note here in the transportation regs, I talked about earlier, the SAE standard, it's the SAG 27 committee, and specifically a series of standards there in the SAE space, trying to address both propagation events as well as external fire events that are imparted onto a battery. So a couple of the different stress sources we talked about, and also looking at potential packaging and shipping means that would help mitigate that if a single battery did go into runaway, you could contain it without actually causing further damage, or at least preventing the takedown of an aircraft or the loss of a vessel or a vehicle. So again, containment being a big key here, that if an event did occur, could you contain it? Could you extinguish it? Could you prevent it from spreading further? Consumer product standards, we have heavy focus on internal short circuits, some of those manufacturing defects that over time you're going to cause the internal anode cathode of the cell to short out, create heat, create unintended current paths. So the forced internal short circuit is a method of trying to emulate some of the more common manufacturing defects that we've seen in the past, of basically a shard of metal that makes its way into the cell. And over time, as the cell expands and contracts during its normal charge-discharge cycling, that shard of metal will essentially work its way through the anode and cathode. And being metal and being conductive on its own, it creates that unintended current path that would lead to a short circuit event, high enough current that it would propagate beyond the cell and not self-extinguish. Crush and impact, I mentioned earlier, that's a fairly simple mechanical way to cause the anode cathode to squeeze together, actually push through the separator, push through the insulation inside a cell, and cause that internal short circuit to occur. One of the bigger concerns with these, is understanding whether or not you've put that short circuit in the right place. EV and eMobility standards, again, concerns with propagation at the larger system level. Generally speaking, when we talk about electric vehicles, we talk about eMobility devices. We may be talking about something like this push behind material handler that I show here, where the user is not on board the vehicle. This is where the user is off board the vehicle, but in other cases, you're on board the vehicle, you're on the scooter, the electric bike, you're on the vehicle. If there's an event going on that you can't immediately see you may or may not be able to easily get away from that incident. The vehicle's traveling. You may or may not have the ability to, if you will, jump off the battery, get away from the battery, get away from the vehicle quick enough. So a lot of the concerns here in the EV and eMobility standards are focusing on external fire. We're focused on some of those mechanical and external stresses that can occur, and whether or not the structure of the vehicle gives you enough protection to allow that passenger to get away in that event. So not only the propagation event, but also the mitigation of personal injury or fatality. How are those being addressed at the vehicle level? I talk about the regulations for vehicles, UNECE R100. We do have an external fire test. We do have simulated crush and crash event testing there to look at how the battery prevents thermal runaway from occurring under those external stress sources. Doesn't address the internal short circuit concerns, but it does address some of those external sources that maybe are beyond the control of the driver of the vehicle. In the US, we don't have a specific EV requirement for propagation testing, so it comes to the OEM manufacturers to address those concerns. For industrial vehicles like forklifts, material handlers, we have in the US ANSI UL 2580, which does have a propagation test where we actually find a way to trigger a single cell failure in a single cell within a battery pack and look at how whether or not it's able to propagate beyond the case of the battery. So now we start talking about specific test methods for propagation. Energy storage, again, a lot of the concern here in North America within the UL 9540 standard, which is for the energy storage system, batteries, inverters, et cetera, enclosure. We have the UL 9540A test method, which has a very prescriptive process for evaluating thermal runaway from the cell all the way through the full installation and considering the fire suppression in the vehicle or the room in construction around it. I mentioned a prescriptive process here. We start with a cell level test. We go through a module level test, then a unit level test, an installation level test with essentially gateways along the way. The cell level test tells us how we can trigger a single cell event. The module level test allows us a small enough system that generally in a lab environment, we can get a lot of good data from this. Even if it did go into a full runaway, you have the ability to somewhat contain this within the laboratory. But depending on how well or how poorly a battery performs at that module level test, you can then take it to the unit or installation level so that if you're showing that you have such a densely packed battery that you can't really prevent cell-to-cell propagation, you have the decision tree. Do I go back and redesign my modules, or does my usage case dictate that I must have that much energy density? I have to have that much capacity, if you will. And I say have to in terms of, you have multiple drivers of why you have a design the way it is. Now we start looking at more of the mitigation and fire suppression means at the unit level and installation level. Does my enclosure allow for sufficient protection that even under a runaway event or a propagation event, the enclosure can contain any potential fire? Can the enclosure include its own fire suppression internal to the battery system so that the battery is self-extinguishing? Or at the installation level, can I consider the overall installation, including ventilation, fire suppression, sprinkler systems, means for fire departments to access the battery to put it out so that I would be able to put out a potential fire at the system level before it spread beyond that installation room. So when I look at those requirements out there, there's a few that really dictate how you run a propagation test to make it somewhat repeatable, but there's still some flexibility there. Again, from a laboratory standpoint, single cell initiation through heating. This, I would say, is overwhelmingly the preferred method. We're creating an external source, so we're not modifying the cell. There's a lot of options out there. It's fairly repeatable, at least at the cell level, to find the right mix of heating surface area, temperature, and ramp rate, temperature ramping that you can trigger a single cell runaway that's somewhat repeatable and somewhat representative of a worst case, at least at the cell level. I show examples here on the screen. You've got module and plug heaters. The one on the upper left for cell based, single cell based battery systems, I can have a heater that's essentially the size of a single cell and use that to be the triggering event for adjacent cells. So I'm not necessarily triggering a single cell into Runaway, but I'm simulating the heat effect of a single cell going into Runaway. So there's a lot of methods here within heating, a lot of ways to get around some of the difficulties of retrofitting or installing these heaters. Some of these thin cell heaters can be somewhat easily installed as part of the manufacturing process of just a test sample. Retrofitting can be difficult depending on how that battery is constructed. It may be difficult to actually go back in, tear the battery apart without causing a secondary issue while you install the heater. So, that's one of the downsides. Depending on your battery design, you may have to try and implement this in the production stage of a single test sample rather than retrofitting a normally produced battery. Penetration method. I see this one requested quite a bit because you can trigger a fairly dramatic event. It can be fairly repeatable, especially if you've got certain types and sizes of batteries where I know I can essentially penetrate anode and cathode at a fairly uniform area within the cell, that I get a fairly reproducible, repeatable thermal runaway event. Smaller cells make this more difficult. Just a few millimeters one way or the other, a few degrees one way or the other of how you penetrate the cell could lead to a drastically different single cell event. And when we're talking about single cell events that's going to be used for a module or a battery level propagation, repeatability, reproducibility is key. We want to see, if you will, a worst case event at the cell level, that when I test it at the cell level, I can have confidence that I'm going to see a similar reaction once I install it in the battery. That when I use the same method of triggering that event, I'm going to get the same level of heat. I'm going to get the same level of flame from that cell. I'm going to get the same directionality of those flame and heat, so that I should be able to give the worst case heating to adjacent cells. It's also versus heaters. This doesn't add additional stress to the adjacent cells by itself. We don't, using a heater, we're not only heating the cell that's under consideration, but we are also heating those adjacent cells to some level. And that preheating might essentially be adding stress that wouldn't be there in a normal single cell runaway event. On larger batteries, like the example here, I showed just drilling a hole in the side of the pack. You're often limited to only penetrating in an externally located cell. Again, may not be a worst case situation because 2 or 3 sides of that cell are essentially heat sinked by the enclosure. If a centrally located cell was to go into runaway, it doesn't have the benefit of dispersing that heat to things other than adjacent cells. So often we want to get a somewhat centrally located cell as our trigger point. Mechanical penetration methods make that difficult. External fire, the projectile test. A lot of times this is used as a way to essentially pre-certify individual cells. If I expose that cell directly to external fire, how bad of a reaction do I get from that cell? So exposing the cell, looking at how it performs under external fire exposure helps me to determine whether or not I need to do a secondary test at the modular battery pack level. Again, from a building code standpoint, we have the first concern that a battery could go into runaway, but we also cause a fire. But we have the secondary concern that if there was a fire from other combustible materials in the building that exposed the battery to that fire, similar to the electric vehicle concerns of a crash event exposes the battery, which is up until that point not experiencing a runaway. Now it's going to see an external fire. Does that trigger the runaway? These are the concerns that we're trying to address here. Nice thing is with a fire, depending on how large the fire is, depending on how we apply it to the battery pack or the cell, it's somewhat repeatable. It may be less repeatable at the full battery, depending on the size and shape of your battery installation. Can you set up a fire test setup such that you get that repeatability? a very small cell like I show here with a single burner underneath it, it's very easy to hit that cell in roughly the same spot, fully engulf the cell in fire for every test. Large battery pack, not so easy. We also have the case where, depending on how you apply that fire, you may or may not be hitting that worst case position on the battery. From a regulator standpoint, that worst case is going to occur in the field. So you need to be sure that you're trying to create that worst case in the test lab. Forced internal short circuit. I talked about this earlier, where you actually put the known simulated shard of metal, and there's actually an L shape that's defined here in the standard, again, from a repeatability standpoint, that you get a repeatable simulated event. However, there's a lot of concern here that because you have to modify an already manufactured cell, it may or may not be representative of what that cell is going to do. You're somewhat taking away the effect of the canister and the pressure relief of the cell from being one of the means of mitigating a short circuit, but it does help you evaluate whether or not the internals of the cell, the electrolyte, the anode and cathode, their construction would create a larger or smaller fire event. From the pros, though, it is internationally accepted. There are a lot of cells that have been through this method. But I would say that often a cell that goes through this method is not able to be reinstalled into a battery pack easily, such that you could utilize that for performing a pack or module level test. Trigger cells, this addresses some of those concerns. If you have a modified cell with that shorting shard of metal inside, modifying an existing manufactured cell generally makes that cell very difficult to reinstall to the battery pack. So there are some third parties that have created a cell that implements that shard, that shorting element into the cell with some sort of a wax layer or other, low melt point separator, such that just by triggering some external heat or creating a little bit of heat to that cell, you'll trigger the internal short circuit and hopefully trigger that thermal runaway. Pros here, it gives you a repeatable trigger method because these are manufactured to be trigger cells. So they're not modified. They're actually put together this way. Some of the original construction, the venting mechanisms, the directionality of an event are typically consistent. And you can actually utilize common cells. The actual OEM cell could be built on the same line with just this modification in place, or for common cell factors, cell sizes, cell types, you could have a fairly similar cell in place. So limited suite of ones that are available off the shelf. So it's not always easy to find a trigger cell that's going to meet your application. Single cell overcharge, electrical overstress. These are sometimes the easiest at the lab level to implement. We just keep charging the battery, bypass any control circuits, and try to get a higher voltage or a higher current into the cell. Generally, once you find a mix of voltage, current, and time that gives you a repeatable event, it's very easy to go ahead and get that event to occur again by directly wiring to an individual cell in a battery pack. But one of the cons, and the biggest con that I've run into, certain cell chemistries that are more robust to overcharge would then require you to overcharge that cell to well over 100% state of charge, and you're really putting much more energy into that cell than would be possible in even the worst case actual event in the field. So I would say you can always overcharge a cell to get to a thermal runaway. Whether or not that cell could ever actually react that way in the field is another story. So easy to implement, but often not very representative of actual worst case conditions. Short circuit has a very similar pro and con. You have it's somewhat easy to implement in a lab environment. You're not pre-stressing the adjacent cells. If you're able to wire directly to that cell, you're just going to cause that cell to go into a a high current mode. Often, many of the cells have short circuit protection built in so that you can't actually trigger a thermal runaway this way. That's great that the cells cannot go into thermal runaway. From a design standpoint, just difficult from a test implementation standpoint. It makes short circuit a pretty difficult method, or makes it difficult to be repeatable if the cell has those types of short circuit protections built in, like a PTC or other venting mechanism that allows the cell to vent before it ever gets into a thermal runaway mode. Module level propagation. A lot of the difficulties here at module level is that you don't address the overall construction of the system. You may have different thermal management going on here at a module versus the full pack. Some of the insulation of the full pack is not really addressed. At the lab level, it's module level testing is easier because you've got a smaller potential event. Containment in the lab, personnel safety is addressed there, but you may or may not get that worst case condition. So that brings us to unit or system level installation tests. And from some building codes standpoint, this is considered the best method. We have to simulate the actual environment. It is potentially the most representative of an actual installation, but it's very difficult to implement in a lab environment. It, of course, costs a lot because you're essentially going to reproduce the entirety of an installation, which may be a one-off installation. So feasibility standpoint, this is probably the worst case for us. From a regulatory standpoint, this may be considered the best case. So understanding that if you can find ways to sell module and smaller system level to evaluate the cell propagation, that's preferred from the lab and manufacturer standpoint. The trick there is that you have to demonstrate to a regulator that you did try to get the worst case actual situation. Understanding we want to make sure we're triggering a single cell to go into runaway repeatably, but we're evaluating whether or not it triggers adjacent cells. If it does trigger adjacent cells, do we prevent spread from beyond the battery enclosure? From a method standpoint, we want to limit the pre-stress of those adjacent cells. So we want the only stress source to be the trigger cell. We want to avoid, obviously, explosion or opening of the enclosure that's going to allow fire to escape. So we want to prevent that visible flame from exiting the battery. Other concerns I just have noted here: additional gas analysis or smoke evaluation. Again, from a building code standpoint, this is an additional concern that makes it more difficult to set up large scale tests, because if the system goes for a runaway, you've got a lot of data acquisition. You've got some constraints there in terms of trying to capture the full volume of any off-gassing. So that has to be addressed. Again, much easier to do at the at the module or cell level. Concerns from a laboratory standpoint, it's very difficult to observe the internals of a large battery system. At the single cell, it's very easy to monitor temperatures, look at it with a thermal camera, look at it with an optical camera. Once you put that inside a module with all the enclosures, et cetera, you're limited to a few data points that you can tell exactly how the cell propagates from one to the other. So partial modules, cell strings, et cetera, adding those extra interim steps to essentially map the progress of a propagation event, and understanding how the single cell propagates to adjacent cells helps you to develop a better module and unit level test. And again, gives you a better case when you're dealing with regulators to show them that I have developed the worst case. I understand my propagation path within my battery. I've designed the battery unit and system to mitigate that risk. So understanding those module, submodule level test results, I would say, is key to demonstrating you have a strong mitigation system in place. We're right up at time here. I apologize going a few minutes over, but understanding that overall propagation is a main concern across the industries. we still have to find ways to address this from a test standpoint. Benefits of doing the testing allows us to categorize or qualify or classify individual cells, module constructions, or systems for different types of installations. Again, most stationary systems are somewhat one-off. So if you have a way to qualify a building block, that regardless of how many of those building blocks you put in the same location, you can prevent spread from one to the other, then that's obviously a best case for us. Understand that the different methods we use, although it may be easier to trigger a single cell event, may or may not be easy to implement, or may not be representative of what happens in a unit or module level installation. Full-scale testing is very difficult to do. Often you're not going to get much value out of that unless you've already done those subsystem level tests and have come to the conclusion that for whatever reason you need to have a certain system design, and you need to rely on suppression or overall installation layout and other engineering constraints to contain a thermal runaway event or propagation event. So for me, as at a test lab, we always are also considering laboratory personnel safety, trying to protect the people and the systems performing the tests. So from our standpoint, we also want to see and understand the cell string, the submodule, module level propagation, how they're actually occurring, so that we have confidence that the laboratory is able to handle that propagation event. With that, I know we've gone over our time, but if there are some questions here, I'd be happy to take them. I will note that we've got the third part of this webinar series going on tomorrow, so you can still register for that. That is more focused on electric vehicle charging standards beyond the core, level 1, level 2 AC charging, some of the different technologies that are implemented out there. With that, I'll leave my contact information on the screen. And Martin, if we've got a few minutes for a couple questions, be happy to take those now.
As always, that was superb. Thank you very much. And we've got a lot of questions, so I'm going to dive straight in for you. First question here is from Jeremy. Can you more clearly define a single fault condition on UL 2580? Does this include BMS limits?
Okay, single fault condition. We talk about that. Yes, it could include BMS limits. Typically, and this is a little bit outside of the normal propagation test, single fault there, we're essentially bypassing
just lost
one
your sound
level
there.
of
Rich, can you hear?
Yes,
okay?
Can you hear me? Am I
yep,
there?
We're good. Yep, go ahead.
Good. Just checking sure I didn't lose my connection. This is a bit outside of the normal propagation event, but single fault conditions, generally speaking, we're bypassing one level of either sensing or control at the battery management system to typically verify that we have some redundancy, that if a thermistor was bad or a software glitch occurred, do you have some redundancy there? So typically just widening the limits on the BMS may be a way to allow for a propagation test, but would not typically be considered a single fault condition.
Thank you. Question here from Alexander. UL 1642 currently includes secondary lithium batteries references. Is that going away?
Yeah, great question. I mentioned it before. I called it a legacy standard. And by that, I meant that it's been around longer than the current UL CSA IEC 62133-2. It's not going away. There are still end products and certain industries where UL 1642 is still required as a way to qualify cells. And I would say more from a general usage standpoint for consumer products, UL 1642 does try to address more of the concerns than the IEC standard does. But I would say that those specific usage cases are dwindling, such that more system level evaluation will take precedence over cell level over testing.
Thank you, Rich. Question here from Kelvin. Can any simulations tools help to pre-scan cell pack thermal runaway performance?
Yes, this is a case where simulation is an excellent tool, because while we may have some difficulty to simulate or model the actual initial cell heat release, when we look at thermal management, we look at where the hot spots are in a battery pack. It is often beneficial, I would say, to find where we think the worst case situation would be. And that helps us to then perform reduced numbers of tests because we've already identified the potential worst case situation. Thermal management modeling is much more mature than individual, I'd say, battery cell modeling. So from trying to simulate what the chemical reaction will be versus understanding where the hottest spot, where the highest level of insulation occurs, it's much easier to model that and then perform a single or a reduced subset of tests to validate that model.
Thank you, Rich. Another question here from Abdul. What steps have you taken to address lab safety?
Lab safety, thanks. So some of the same concerns I talked about in the building codes. Typically, in our case, we start with ventilation. Regardless of the test you're doing, do you have sufficient ventilation to basically allow for any off-gassing, any smoke that occurs to be, if you will, directed away from personnel and especially other office personnel? Secondly, barriers. So just having some level of barrier between the test engineers, of course, people that are not related to the testing activity, that they're isolated from the test that's underway. And that level of barrier would increase with both the severity of the tests, the hazards involved with that test, does require some level of risk assessment. And I would say that beyond that, when you get to larger and larger batteries, understanding the potential for a full-scale fire event, then you start looking at how well you isolate just that test pad, that test room from other rooms. So you've actually getting into outdoor or remote facilities with their own dedicated air handling. And in some cases, it may have to be essentially an open air test site because you just don't have a way to fully contain that test. Again, that requires usually some coordination with local fire officials, fire marshal, et cetera, to even permit just for that one test, or I'll have them on hand to handle the events that occur. So as you get larger and larger events, we just basically add those different layers from ventilation to barriers to separate enclosures to separate literally facilities from other activities and other personnel. Thank you for that.
Thank you, Rich. A question here from Liz. Are you seeing any requirements related to smoke toxicity? Often materials that are excellent for protecting against thermal runaway also decompose and create toxic gases.
So that is, I didn't really address that much here in today's presentation, but that is another area of, I would say, much discussion and some concern. Often with gas analysis, you somewhat have to know what you're looking for. You have to know which gases of concern you're dealing with. When a battery combusts or burns, as you mentioned, a lot of the concerns, a lot of the chemicals that we're concerned with within a lithium battery don't tend to make it into that off-gassing during a fire. They're consumed or they're left as residue, but not necessarily part of that off-gas. And then when you add those other materials, insulation materials, enclosure materials, other nearby combustibles or non-combustibles, plastics and polymers and things, the constituents of those going into combustion greatly contribute to the potential toxicity of that gas. On a simple side, I would say that we try to look for more of the common EPA clean air type of test panels. Your more common 4-gas meters where you're just looking for lower explosive levels, lower flammable levels. You're looking for oxygen content in the air from a suffocation hazard. Those tend to be the higher concerns for most combustion events. But I think as different chemistries are utilized and come into play, we do have to take a deeper look at some of those gases of concern. The UL 9540A test, for example, attempts to volumetrically capture the gases that are released from a battery and doing a more extensive, gas chromatography test to hopefully identify more than just certain constituents of interest. The concern there is You're collecting that data, you're presenting that data, but you're not really setting limits. A building inspector may or may not even know what they're looking at there. So there's still some work to be done there in terms of deciding what's an acceptable or unacceptable level of off-gassing and what's in that gas.
Thank you, Rich. Question here from Connor. Have you tested many SSBs? Do you have a general view on whether the safety promises can be achieved?
I'm sorry, SSB. I'm not sure what he's referring to there.
Connor, if you could elaborate on your question, I'll ask it if you can type in for me. Okay, I'll move on. Next question from Warden. Do you do complete battery pack tests for electric vehicles? And if so, do you see flames escaping the battery pack during the tests? Would this be required by OEMs?
So, great question. When we talk about doing this testing for automakers, generally the OEMs are making their own requirements. In the case of, I mentioned that the U.S. FMVSS is very light on regulations here, but there are requirements under a crash event, primarily that even if a flame did escape from the battery, whether or not it's shielded from the passenger compartment. So passengers in a vehicle, the number one priority is shielding them from any potential fire that occurs. So I would say that at a vehicle level, we address where does that flame potentially propagate to, more so than we worry about just a flame being visible outside of the battery pack. Stationary batteries, because we don't know what adjacent combustibles might be there, we focus more on visible flame. I see that Connor did reply on the
solid state
SSB, meaning solid state. Yeah, done much less testing on solid state batteries to this level, mainly because from a commercialization standpoint, there's been less that are ready to go for, say, a megawatt installation or an EV application. Most of the work that I've done personally there has been at the single cell level, and it's really been more focused on performance. So I know that some manufacturers and some labs have probably done a bit more testing on seeing how they do perform. Generally, of course, is a lot more promising, but I haven't seen them at large scale for doing a full test like this.
Okay, thank you, Rich. Right, I've got a four-parter from Dominic, so I'll quickly go through it. Number one, which standard is currently under rework, UL 9540A or UL 9540?
So they're both under, I would say, somewhat constant revision. There are current, additions available, but I would say that that committee it's a joint committee 9540 writes the 9540A standard. There's a lot of activity, I would say, ongoing. So expect multiple iterations as we get more batteries in the field, as we get more test reports out, as of course we get potential incidents that occur in the field or close calls in the field. The first responders, the regulators, the electrical inspectors, the fire marshals, are all feeding back into that committee to help determine what's the best course of action. And on the other side, we have the manufacturers, the test labs, and some of the users looking at what do they see from a feasibility, what are they actually experiencing in the field with their own products, to adjust either the test method for propagation or the actual construction requirements for the battery within 9540. So both are definitely under, I would say, consistent proposals for change.
Do you know what the main topics will be when changed during the rework?
Again, everything related to propagation here. With 9540A, it comes into some of the analysis methods. The gas analysis I mentioned there is somewhat loosely defined. So, we do see some differences in how data is presented and whether or not an inspector can go through that data and understand what they're looking at. So I see a lot of the data presentation, which is going to then change some of the methodologies used to collect that data as being the bigger changes there. In terms of how we implement the test, heating as the preferred primary method is I see fairly stable right now. It's a bit more in terms of how we collect the data and how we present the data. On the 9540 side, I would say more of the changes are tied to the NFPA 855 building code standard, so that where specifying the batteries in accordance with changes that occur there. So, and we talk about 9540, 9540A, but the third part of that is the NFPA 855 building code standard, which gets into the installation of the battery system. So those all three kind of go together, and they're, again, because of the constant proposals on all three of those, they're going to have an effect where a propagation effect, if you will, of causing the other standards to update at the same time.
Do you know when the new standard will be released?
Those tend to be on a several month cycle. I don't have a timing for the immediate one, but I would expect some revision here in 2022.
Okay, final one from Dominic. Will UL 9540A also linked to UL 1973?
So there's a little bit less of making changes to 1973 based on those, because a 1973 as a stationary battery that has other applications could be more of a standalone battery standard rather than just a component of a 9540 system. So I would say that more likely we'll see caveats added in 9540 that have to be considered more than we'll see modifications to the 1973 battery standard.
Okay, thank you. No one from Wolfgang here. He says, hello, UN 38.3 as well as IEC 62619 offers cell testing as an alternative to battery testing. Do you think alternative cell tests gives suitable results regarding behavior of large batteries?
So I would say first that the UN 38.3 requires cell and battery level tests. So a cell test would not be considered sufficient to address battery level tests. There is there's an internal short circuit test at the cell level in UN 38.3. That is really just verifying what type of I would say result would occur from a single cell thermal runaway, again, and not yet addressing propagation at the battery pack level. The IEC 62619 also has heavy reliance on doing the stress tests at the cell level, and then more mechanical system level tests at the system level. I would say that the concern there, especially on the IEC standard side, is that you have to consider the final application. Where is this installed? And that application standard should fill the gaps in terms of what other evaluation has to occur. So if that 62619 battery is going into a forklift, the forklift standard should address that more completely. And I would say it is known that there are some obviously gaps in some of the standards, trying to, if you will, get a standard out there that even though the technology and the applications are changing every day, standards update at a much slower pace.
Thank you. Another question. Is there a maximum temperature to which a cell will be heated?
No, we don't have a specific limit for heating in these test methods. The expectation is that at the cell level, doing some iterations of temperature, surface area of heating, ramp rate of that temperature, whether or not that cell is already at 100% state of charge or a lower state of charge. It's difficult to try and find that. I call it sweet spot of getting a repeatable event. So the short answer is you've got multiple iterations to find the best mix of temperature, ramp, and coverage for the cell.
Thank you, Rich. Another question. Where can Intertek test UL 9540A?
So, yeah, this is a specific question to us. We have a few sites that are underway. We currently utilize some partner facilities to implement that test offsite. So not currently at an Intertek site, but witnessed by Intertek engineers so we can issue our own test reports. We do have a few sites globally that we have kicked off, but those are still a few months out.
Thank you, Rich. Okay, final question for you, Rich, from Matt. And the question is there a specific standard or standards that address protection for vehicle and eMobility products?
So the different applications have different standards. There's a lack of harmonization there. even across what we call eMobility devices. Hoverboards a few years ago kind of triggered a wave of standardization addressing some of the concerns there. Electric bicycles are another, very specific subset of eMobility that has its own, multiple standards panels, because the overall vehicle, if you will, of a personal mobility device, we call it, if it's a wheelchair, if it's a bicycle, if it's a scooter, electric car, a forklift, that end product tends to have different regulatory authorities in regions, especially in the US, for example. And so what that tends to do is leads to some non-harmonized activity in trying to address down to the battery concerns specific to that product. So unfortunately, there's not an overriding e-mobility standard for batteries, but rather the work of multiple people that sit across those committees trying to get each committee, each standard to somewhat adopt some of the changes that have occurred elsewhere. Similar to that, the three I mentioned earlier for building products, it's an ongoing process. It's just kind of inherent to the consensus standard writing process, that you have to have buy-in from multiple stakeholders before you make those changes or carry those changes over from one industry to the other.
Yeah, Matt just came back in with specifically structure protection for thermal events, from thermal events.
Yeah, again, in the vehicle space, we typically just have the requirement that you must prevent any flame from that battery or electrolyte from that battery or high voltage components from that battery from penetrating or being accessible to the passenger compartment. There's really no definition of how you need to do that. On the U.S. side, from the National Highways, NHTSA, National Highway Safety Traffic Administration, they intentionally do not want to dictate how you make that happen, but rather define the results they expect to see, and the OEMs would therefore be free to design that mitigation tactic any way they want. So I would say from the regulatory standpoint, we try to there's the attempt to be less prescriptive about how you specifically implement this, and the looking for some new designs to basically help create that situation. If there was an easy fix that seemed to be consistent, then they would probably be more prescriptive. But I think there's still enough design variants out there that we're not going to see that defined so well yet.
Okay, Rich, look, you've just answered 19 questions, so I'm going to round it up to 20. Got one here from Paul. How important is the venting arrangement in preventing runaway? Some cells seem to need a specific orientation, e.g., not upside down, for the venting to work.
Right. That's something that I do see quite a bit. The cell layout, if you're able to arrange the cells such that adjacent cells can't somehow vent into each other, especially when you run into a true thermal runaway where that vent is not percolating a flame, but actually going alongside as the first point of exit of that flame, meaning it's going to be the hottest spot during a thermal runaway event. So yeah, performing different orientations so that not only physically shielding one cell from the other, but also orienting them so they're essentially facing in opposite directions is something that I do see quite a bit of effort put into. So yeah, definitely cell orientation, venting locations, the intended venting propagation event is should be addressed, I think, highly. And as I mentioned earlier, from a test lab standpoint, doing the single cell to a multiple cell subassembly submodule where we can actually monitor from thermal image, from optical image cameras, and see how that propagation event moves from one cell to the next, helps us to see what we expect to, what we would expect at the larger scale test, and helps manufacturers to address some design concerns up front rather than just performing the full scale test and essentially having to make some guesswork as to how the failure actually propagated through the battery.
Rich, as always, thank you for a fantastic Q&A session. That was brilliant. Thank you, sir.
Thank you very much. Appreciate everyone's time here. Again, my contact information on the screen. Please feel free to reach out to me directly.